Welcome to lesson 2 in my playlist concerning graph theory. In this lesson, I'm going to talk about some examples and I'll also do a few proofs. Section 1, definition of a simple graph, graph archetypes, digital skeletons, and the handshaking lemma. I want to define something called a simple graph. This is a type of graph that we're going to be talking about mostly in the rest of this lesson and the following lessons. There are three conditions to be a simple graph, and this graph on the left violates all three. This graph on the right does not. This is actually a simple graph. So let me go through the three conditions. One is undirected. So you can't have a directed edge like this here where you notice the little arrow. That means the relationship is between here and here. For example, an airline flight, maybe this graph represents flights between cities. And this is just showing a flight between this city and this city going in this direction. So that's not allowed in a simple graph. Then there's no loops. You notice we have a loop in each one of these vertices going back to itself. That's not allowed. And then no multiple edges, and again, it's violated here. Between every two nodes, you have multiple edges, and that's not allowed in a simple graph. So here we have a simple graph. There's no loops, there's no directed edges, and there's no multiple edges between any of these vertices. Okay, so the term simple is maybe a little bit misleading because you can get into some fairly complicated situations and still be a simple graph, but these non-simple graphs are even more complex. We have multiple edges and loops and so forth, which they can be useful also, but we're taking the simple case here for the most part. On this slide, I have examples of three different types of graphs. On the left, we have what's called a complete graph, and for a set of vertices, you have edges between any two of them. So all the vertices are adjacent. This particular one is called K5. If you had K6, you'd have another vertex with all of these vertices having an edge to it directly. And these are called complete graphs. Then you have cycles like this here. This is C6. You could have C3, with just three of them. And of course you could have more, C7, C8. And then we have the bipartite graph on the right. This is called K33. The 3 stands for the 3 vertices on the left, and the other 3 stands for the 3 vertices here. And the condition is that you have two sets of vertices, and you have full connectivity across the set. So, for example, this vertex here has an edge to every vertex on the other side out of the other set, and then this vertex here has an edge to every other vertex on the other set, and the same thing on this side here. However, for the set on the left, there's no edges between these vertices, and for the set on the right, there's also no edges between these vertices. That's called a bipartite graph. And as I say, this one's K33. If I had K43, then you'd have another vertex up here that would be, I can even draw it in. So you'd have a vertex here, and then you'd have an edge to each one of these like that. And it would not have an edge with any of these other three here. So that would be K43. Okay, so these are common examples that you'll see come up in different instances. There's more than one way to represent a graph. On the left, we have the way we've been talking about. A, B, C, and D are vertices, and then the edges are at blue here. Another way of doing this that's equivalent is called an adjacency matrix. So you can see here for A, just looking at this first row, A doesn't have a loop, so it doesn't go back to A, but it has a 1 in these positions B, C, and D, and it has an edge to B, C, and D. So we have that here. Let's look at D, the last row here. So D, again, doesn't have any loops, so there's a 0 in here. And then it has an edge to A and C, but not to B. So you have a 1 under column A and a 1 under column C, but not under B. So for a simple graph, you're always going to have zeros here across the main diagonal because, as you recall, loops are not allowed for simple graphs. And then they're also symmetric for simple graphs because simple graphs are unidirectional. So everything is symmetric here. If you have an edge between D and C, then that's also between C and D. So you have, for example, C and D there's a 1 here, and D and C you'd have a 1 here because of the symmetry. Okay, so you'll see this in some cases. Sometimes it's more convenient to write things like this as opposed to a graphical representation. The handshaking lemma says the sum of the degrees of the vertices of a graph equals twice the number of edges. You can see that if you just look at one of these edges here. When you count the degree of this vertex here, you're counting this edge once. And then when you count the degree of this vertex, you're counting this edge a second time. So when you go around the whole graph, you end up counting the edges twice. We also have a corollary. The number of vertices with an odd degree must be even. That follows because the sum of the degrees of the vertices has to be even. So basically you take the vertices that have an even degree, and when you add those together you get an even number. And what's left are the vertices that have an odd degree. And in order to get an even number from those, you have to have an even number of odd numbers in order to get an even number. I'll explain that a little bit more on the next slide, but that's how this corollary follows. Just to clarify a little bit and to repeat what I was saying concerning the corollary. When you add even numbers, of course, you get even numbers. And so for the vertices that have even degree, when you add those up, you get an even number. The question is the remaining vertices that have odd degree, how does that play out in terms of ending up with an even number? So I'm just showing here if you had 2 vertices of odd degree, when you add those together, you get this here, and then you can factor a 2 out of this, and so you get an even number. And that'll happen the same if you had 4 or 6 or any even number of odd numbers, you always get an even number. But if you have an odd number of odd numbers added together, and that's what I've shown here, odd numbers are always of the form 2x plus 1, 2k plus 1. So you have 3 of them here, and when you factor things out in combined terms, you basically get 2 times k, 2 times n, 2 times n, and then you have 3, but you take 2 out of that and put it in here, and then you have 1 left over. So this is of the form of an odd number. And the same again happens if you have 5 or 7 or any odd number of odd numbers. When you add them together, you get an odd number. So in order for the sum of the vertices, the degrees of the vertices of a graph to be even, you need to have an even number of vertices of odd degree. So either 2 or 4 or whatever it happens to be, 6, and so on. Okay, so let's continue. I have quite a bit more in this lesson. Section 2, trees. A tree is another type of graph. I have an example here on the right. And the definition is here. A tree is an undirected graph in which every pair of distinct vertices is connected by exactly one path, or equivalently, a connected acyclic undirected graph. In other words, a graph that has no cycles but is connected. So these 2 definitions are equivalent. Then if you have more than one tree that are basically unconnected, That's known as a forest. We have a theorem related to trees, which I'll prove in the next couple of slides. A tree with n vertices has n minus 1 edges. So it's a very efficient way of connecting vertices together. It's the most efficient way, actually, of connecting a set of vertices together. If we cut the tree by removing an edge, so let me show that. If we remove this edge here, then what you get are two trees, a disconnected graph. So you have this tree here, and then you have this tree here. And that's true no matter what edge you remove. You'll get two trees, which is, by our definition, is a forest. There's a unique path between any 2 points, any two vertices on the tree. So if we wanted to go from here to here, there would be one path, and that would be going from here to here to here, and then down to here. And then the other point I want to make is these vertices at the bottom that have only one edge, as opposed to the other vertices which have two or more. These are called leaves. So this has one edge, it's a leaf. This is a leaf. This vertex is a leaf, as is this one and this one and this one. On this slide, I want to prove that a tree with n vertices has n minus 1 edges. We'll do the proof by induction on n. We need to prove a base case. For n equals 1, a tree with one vertex has 0 edges. In other words, it has one less edge than the number of vertices. We don't need to prove a second base case, but I'll do it since it's kind of easy. For n equals 2, a tree would have 2 vertices and 1 edge. And again, that would be 1 edge less than the number of vertices. The induction step, the hypothesis, assumed that every tree with k vertices has exactly k minus 1 edges for arbitrary k greater than or equal to 3. Then the inductive step, let T be any tree with k plus 1 vertices. We must show that T has exactly k edges. And then we'll be done. That's the induction. So because T is a tree with 3 or more vertices, it has at least one leaf. For if every vertex had degree greater than or equal to 2, there would be a cycle which would contradict us having a T being a tree. I need to prove this, that's why I put it in bold and in blue, and I'll prove that on the next slide. So let V be the leaf of T, or there could be more than one, but there's at least one. And let U be its unique neighbor, so it's adjacent to V. Remove V and the edge UV from T, and we get another set, another graph, T prime. We don't know it's a tree yet, but we'll show that it is. So T prime has k vertices, since we removed V from it. T prime is still connected. If it were not, otherwise T would not have been connected in the first place. And we know it is because T is a tree. We've just removed the pendant edge, in other words, an edge connected to a leaf. So that should not change its connectivity. T prime has no cycles because T had none and we only removed the pendant edge. Therefore, T prime is a tree with k vertices. By the inductive hypothesis, T prime is exactly k minus 1 edges. But T had exactly one more edge than T prime, namely the edge we removed, UV. So T has k minus 1 plus 1 equals k edges, which is what we needed to prove to finalize the induction. On the next slide, I'll prove this here. This is not obvious, so it'll take a little bit of effort to prove it, but I'll do that on the next slide. On this slide, I want to prove the statement I mentioned on the previous proof. Let G be a graph where every vertex has degree greater than or equal to 2. I'm using this notation here. Degree of vertex V is greater than or equal to 2 for every vertex in our graph. Then G contains at least one cycle. Okay, so it's fairly straightforward. It's a little bit long, but it's fairly straightforward. Consider a path P in the graph G that is of maximum possible length. Keyword here is A, so there could be more than one, but we'll pick one such path. Let us denote this path by the sequence shown here, V1, V2, Vk, all the way up to Vk, where k is the number of vertices in the path. Focus on the last vertex in the path, V sub k. By the hypothesis, its degree is greater than or equal to 2. Since its degree is greater than or equal to 2, it must have at least two neighbors. One of them is the neighbor just before it, V sub k minus 1. And then there's another neighbor that's other than V sub k minus 1, which we'll call U. There's two cases for U. Either U is not one of the vertices in this path, and in that case we could form a path V1, V2, V sub k up and then add U to it, but then this would be a path longer than what we assume to be the maximum path, so that would be a contradiction. The other case is U is one of the vertices in the path. Let's say it's V sub I, so it would be somewhere between V sub 1 and V sub k minus 2. Since U is a vertex V sub I somewhere earlier in the sequence, the edge V sub k, V sub I connects the end of the path back to an earlier part of the path. This closes a loop formed by the path segment V sub I sub 1, V sub k, and then V sub k connects back to V sub I, and that gives us a loop. And that's what we wanted to, or a cycle, that's what we wanted to prove. Okay, so not that easy. It was kind of, if you want to go through all the steps in the proof and be thorough, it takes quite a bit of effort. So there you have it. So I have a few more slides, and let's continue. Section 3, Planarity. A graph is planar if it can be drawn in a plane such that no two edges intersect. And I have an example of a planar graph here. Just to give you one that's not planar, a K5, which we saw earlier, there's no way of drawing that even when you rearrange the edges in the vertices without having intersections. So that would be an example of a non-planar graph. Then in conjunction with planar graphs, we have this formula, it's called Euler's formula. It was discovered by Leonhard Euler. Actually, I think it was known before that, but he is given his name. And it says that the number of vertices minus the number of edges plus the number of faces enclosed by the edges and vertices of the graph always equals 2. And you can see from our example here, we have 8 vertices, we have 12 edges, so that would be minus 4. But then the faces, including the outer face or outside of the graph, that's 6. So when you add all those up, you get 2. And that's always true if you have a planar graph. How do we tell if a graph is planar? I have a simple example here. On the left, I have a graph, and it looks like it's not planar because these two edges cross each other here, and that violates the definition. However, that's not sufficient to claim that it's not planar, because all you need to do is take this dot here and just pull it down, as I've shown on the right, and you have the same exact connectivity. This dot has an edge to these other two dots, same here. Then this red dot is connected to these two. So for a more complex graph, it's not easy to see if it's planar or not, because you can have a lot of these crossings which are not necessarily needed. So you can try to untangle it, I should say, and if you can get it into a form where there's no edges crossing each other, then you know it's planar. However, you may not be able to do that, and there's another method which I'm going to show you in the next few slides that can also help to determine that something is not a planar graph. The two graphs that I'm showing here on this slide, K5 and K33, which we've seen before, if either one of these appears in a more complicated graph, the graph is non-planar. Now, the way these can appear can be disguised, and it can take some effort to figure out if one of these, or both, in fact, appears in a particular graph. So I'll talk a little bit more about that in the following graphs, including a theorem that kind of says what I just mentioned here. We have something called subdivision on this slide, and its opposite is helpful in determining whether we have a K5 or a K33 within a more complex graph. So subdivision is pretty easy. If you have an edge in a graph and you add vertices like this, or even worse, like this here, so these are new vertices to the edge UV, this doesn't change whether the graph is planar or not. Now you can also go in the other direction, and that's called smoothing, where you remove vertices within an edge. So we can go from here to here to here, and again, you don't change whether the graph is planar or not by doing that, but it may make it more easy to see if you remove some vertices that you have K5 or K33 embedded. So I have a simple example here. I squeezed in at the top, and this has these vertices here that we might want to smooth out. So on this edge here, I want to remove that vertex, and on this edge here, I want to remove this, and then on this edge from here to here, I'll remove that. And then you can see that that would be K5. So this is a simple example where you have a slightly more complicated graph than K5, but by doing this smoothing, you can see that it's K5. I have a little bit more complex example that I'll also show you where you can determine whether the graph is non-planar. So just to emphasize the point about the inverse of subdivision, I have a slide here on smoothing, although we talked about it a little bit on the previous slide. So smoothing is the inverse of subdivision by iteratively suppressing the degree 2 nodes within a path. We, so to speak, pull the strings tight. If the remaining structure forms K5 or K33 or is part of the remaining structure, the original graph is non-planar. So the key point here is you can remove this if it's degree 2. If it had some connection outside of this, then you may be changing whether or not the graph is planar or not by removing it. But as long as it's only of degree 2, you can remove it, and then you have this edge here replacing this, and the resulting graph has the same planarity or non-planarity as the graph you started with. What we've been saying concerning the K5 and K33 being a subdivision of a graph, and that implying that the graph is non-planar, is something called Kuratowski's theorem. I just took this definition here from Wikipedia, but as I say, this is just formalizing what we've been talking about in the last few slides. So I'll just leave it here for a second in case you want to read through it, or if you want to go to the Wikipedia article and get some more information on it. And the other thing I'll mention is there's also something called Wagner's theorem, which is similar, it's equivalent to Kuratowski's theorem, but it gives you another methodology of determining whether or not a graph is planar or non-planar. I'm not going to cover it here, but I just thought I'd mention it just to make you aware of that. The graph shown on this slide is known as the Peterson's graph, and it's used in a lot of counterexamples. The reason I have it here is I want to show that it's non-planar using the smoothing that we talked about, and I'll show that it actually has K33 embedded in it or hidden in it. And I'll do that on the next slide. On this slide, I'm going to show that the Peterson graph has embedded in it K33. The first thing we'll do is we'll take a subgraph out of this by removing this edge and this edge. So if the subgraph has K33, then the containing graph would also contain K33 and thus be non-planar. Going from here to here, I didn't change any structure. I just put some color to the different dots. And then I want to smooth out 4 different paths. So this path here, we can remove the black dot and get this edge. And for this path here, we can remove the black dot and get this edge. And then from here to here, we have another path, and we can remove this vertex and get this edge here, and then the same thing here, and get this. And this is K3. I can rearrange it a little bit to make it clearer, but you can see here that none of the blue vertices are adjacent to each other, and none of the red vertices are adjacent to each other. However, each blue vertex connects or is adjacent to each of the 3 red vertices, and each of the 3 red vertices is adjacent to each of the 3 blue vertices, which is by definition K33. It turns out that the Peterson graph also has embedded in it K5. You may want to see if you can prove that, starting with this here, using smoothing or subdivision. Section 4, the Eulerian condition and summary. I want to come back to the problem we talked about in the first lesson, the Königsberg bridges. And to do that, I want to define a term first. It's called a trail, which I have here on this slide. A trail is a sequence of vertices in a graph such that the 3 conditions hold here. Each consecutive pair is connected by an edge in the graph. No edge appears more than once. So this is sort of like our bridges. We didn't want to cross the bridges more than once. And vertices may repeat. So you can go over, in our bridge problem, you can go over the same land masses more than once. Only edges are forbidden from repeating. So the added condition that we had for the Königsberg bridges was that you end up where you started. And the trail doesn't require that. A trail just says you can go from one point to another without repeating any edges, but you can cross the vertices more than once. Now we have the Eulerian condition, which is what we want for our Königsberg bridge problem. An Eulerian circuit is a trail that traverses every edge in a graph exactly once and returns to the start. So it's a trail, and then it has this additional condition of returning to the starting position. And then we have the theorem, which I mentioned in the first lesson, but I just want to emphasize that this holds in general, not just for the Königsberg bridge problem. A connected graph has an Eulerian circuit if and only if every vertex is of even degree. And I copied over the example from the bridge problem where we adjusted it so that every vertex had even degree. Notice this is 4, 6, 4, and 4. And then the green numbers here was just the Eulerian circuit. We didn't use that term in the lesson, first lesson, but that's what this, if we go from 1 to 2 to 3 to 4 to 5, 6, 7, 8, and then 9, that's an Eulerian circuit. So you start at A and you end at vertex A. I have sort of a sketch, I guess you would say, of the theorem I stated on the previous slide concerning the Eulerian circuit. I just have a vertex here. Assume an Eulerian circuit exists. The observation is, let me point to these, to pass through a vertex V without stopping, you need one edge to enter and one edge to leave. The implication is the edges must come in pairs, and the conclusion is the degree of every vertex must be even. Okay, so that's not a formal proof, but it gives you an idea. Wherever you go in, you need to come back out, and since you're requiring that you return from where your starting point, that means you leave the starting point and then you come back to that at the end, so it requires that to be even also. Okay, so as I say, this is kind of a more of a hands-waving proof, just to give you some intuition as to why this is true. We have a summary of what was in this lesson. First we talked about simple graphs, which will be the main focus of the following lessons. We'll stick to those. And if you recall, they had no loops and no support for multiple edges between two vertices. Then we talked about the handshaking lemma, where the sum of the degrees of the vertices equal twice the number of edges. Then we had a theorem about trees, which took quite a bit of effort to prove that trees with n vertices have exactly n-1 edges, and this is the most efficient way of connecting n vertices. Then we talked a little bit about Euler's formula. Remember, this was the vertices, edges, and then faces enclosed by the graph, and we had to add in the one face that was exterior, and these numbers always added up to 2. And then we talked about the planarity, whether a graph was planar or not, and we looked at some examples where if you're able to find an embedded K5 or a K33 in your graph or a subgraph of your graph, then that meant the graph was non-planar, which means you can't draw it in a plane without intersecting some of the edges. And finally, I just have some examples of where graphs are used. This is just a small list. You have computer networks, and I would add even telecommunication networks, where you typically have graphs in the processing units in a computing network are the vertices, and then the connectivity between the processing units are the edges. And then you have social networks. We talked about the handshaking theorem. That's just one example where you would model interactions between people using graphs. And then, of course, in chemistry we have atoms and molecules, where we essentially are using graphs to show how they're connected together. And then some of those cases are actually multigraphs, right? You may have more than one bond between two atoms, so you would need multigraphs in that case. Okay, so that's the last slide in this lesson. As you probably noticed, I'm using Notebook LM, and with mixed results. It's more of an experiment. Hopefully it wasn't too choppy. I ended up deleting a lot of the Notebook LM slides. Some of them were just wrong, and some of the ones that were more useful I kept. And then I inserted slides more to my style to fill in some of the gaps. And the other experiment I did is I put section headers in the document. I'm hoping that AI will be able to pick those off and then give me the timestamps, which I can put into the description for the video. So I don't know if that's going to work or not, but you'll see when you get to the description. Okay, so I have a few more videos coming after this. I want to look at some of the classification of the simple graphs, excuse me, and then I have a little bit more after that. So maybe another 2 or 3 videos on this topic.